order to continue our discussion on the existence problem, we still need some important result that I mentioned at the beginning, at the end of the lecture of yesterday. So let's start with the discussion on the Harnack inequality. Let me rewrite it and complete the proof that we made yesterday. So we have a ball B R ball centered at 0. Consider the ball R, the open ball, and let U be harmonic ball. So let me denote it just by BR. And let suppose that U is larger or equal than 0, the crucial assumption, and then take any R in between 0 and R. Okay, then we have that U of X U of 0 here. Then we have 1 plus R over R divided by 1 minus R over R. 1. Here we have changing this this is the statement that I think we wrote yesterday. Okay. As I told you yesterday, so we have a big ball. So we have also the small ball. And we take an intermediate ball. I think yesterday I call it ball of radius rho. If it is not the case, please tell me, because I don't remember exactly the notation of yesterday, but I think that this was rho. And then at the end, this is just an auxiliary ball that will be disappear at the end. Indeed, this, sorry, for any. This statements depends on 2 radi, not on 3 radi. Okay, so at the end, this auxiliary ball we will let rho to R. Okay, and this will disappear. Okay, we start the estimate, as we said yesterday, by writing the Poisson integral formula. Poisson integral formula mediating over this intermediate ball. And we do this formula for X in the small ball. So we consider the mean value on the ball rho. Okay, so this is B rho. So we have rho square minus x squared. Then recall, here we have a constant normalization factor. Here we have just one rho. Here we have x minus y to the n. Oh, yes, by Poisson, and observing that u is so we can write u of x for any x in the closure of the ball, of the small ball. Okay, well, then as we saw yesterday, we take a point here. So we use this formula for x on the boundary of the small ball. So this means that for the moment the norm of the vector x is exactly equal to r. So here we have x, y is running on the boundary of the intermediate ball, so y is here, and then we look at the distance, because we want to eliminate this denominator, and so we have to bound from below and from above this denominator in order to get both the inequalities. So let's start to bound it from below. So this distance here is surely larger than or equal to this distance here, which is the difference rho minus small r. Okay, and so in this way, this integral is less than or equal, so let me call it, this integral, let me call it star. So this says that for any x on the boundary of the ball, star less than or equal to, and then just copy the first term here. Then we have here 1 divided by rho minus r to the n. The integral on the boundary of the ball of radius rho, u of y. Okay. Actually, this is equal to r squared. So let me just replace this with r squared. Okay. Rho minus r, and then here we want to make it the mean value, the surface mean value formula. Okay, so we multiply and divide by rho to the n minus 1, divide it here by rho to the n minus 1, and put this constant here. So this is exactly, therefore, this factor here one of the rho minus r cancels with this, so rho plus r, it remains rho plus r, divided. This rho remains. Then we have rho minus r to the n minus 1. And then using the surface mean value formula, if I'm not wrong, rho multiplied by rho rho plus r, rho to the n minus 1, okay. Be rho to the n minus 2, rho plus r divided by rho minus r to the n minus 1, 0. So, how can we write this? We can write in various ways, but I wrote it 1 plus, so we have rho times 1 plus r over rho n minus 1 minus r over rho 1 equals 0. So this cancels with this. Please check the computations if I'm making some mistake. Now letting rho to r first inequality here. Okay. Is it clear?
Yes.
Okay. Now let's see the opposite the other inequality here. It's clear the proof we should change this and find an estimate from above. So the estimate from above so this is less than or equal than in the case rho plus r. So let's try to go quickly. So what happens here? Well, we have larger or equal than rho square minus r square divided sigma n minus 1 rho. Then we have 1 divided by rho plus now, no? Because we are using the inequality, the other inequality, so rho plus r to the n. Then we multiply and divide by, as before, this. Here, of course, as I said also yesterday, I'm always using this assumption. The assumption has been used in doing this inequality here and in doing this inequality, okay? Okay, so now what's happening here? What cancels here is rho plus r. So here it remains rho minus r, differently from before. So what remains is the minus now. On the other hand, here we have, so I put this sigma n minus 1, this factor, I put it here. So this becomes rho plus r to the n minus 1 equals 0. And now the computation is the same, just divide by rho, let, and similar. As before, rho converges to r gives inequality 2. Okay? This is one first inequality that we we have proven. So this concludes the proof. Now we want to see other forms of this inequality and its applications, and then finally we will go to the description of the Perron method for solving the Dirichlet problem. So if this is clear, maybe one remark. We will typically use this. The conclusion is, okay, sorry, I missed. So this happens to be inside the ball, but what I did is just inequality on the boundary of the small ball, but by the maximum and minimum principle, the inequality remains true also inside the small ball. No? So, sorry. So inequality true, 1, 2 holds on the boundary. Then maximum and minimum principle for harmonic functions, weak maximum and minimum principle, implies that 1 and 2 are hold in BR. Okay. I think also yesterday we said this. Okay. So typically, maybe remark. So you see, what's important here is to actually to do the estimate just for points on the boundary. So typically, 1 and 2 will be applied when R is equal or X equal R. Okay. So we will put here norm of X, norm of X, norm of X, norm of X. Okay. So this is an estimate in an interior ball. Let's see now other ways of there is already a corollary here. There is already an important corollary, actually. So corollary, maybe, before going on, it's very interesting. Let U be harmonic Rn. Suppose that suppose that there exists a constant k such that U is larger or equal than k. Rn. Then U is constant. I think that this on entire solutions we have already seen something like this. Do you remember when we have seen something similar to this result? This was called, remember, Liouville type theorem, no? We have seen something. Now this is, and do you remember the typical assumption for having, so suppose you have an entire harmonic function in the whole space. Typically, we assumed that U was, in order to get that U is necessarily constant. Do you remember this rigidity result? We assumed that U was, can you remember this? In order to get Liouville. Maybe Rahama, do you remember? It was a consequence of the gradient estimate. Wow. U was supposed to be Bookchin maybe knows.
Yes, we have studied it, but I cannot remember conditions just now.
Bounded, no? It was bounded. Do you remember? Because why it was bounded? Well, because the gradient estimate was saying something. You can bound, say, the gradient of u times some constant divided by r in a ball, say, and the infinity norm of u. So something like this, say, no? Something like not. We wrote this more precisely, but then it's enough to let this to plus infinity to get the gradient must be 0, no?
It's analog of Cauchy inequality in complex analysis.
Of course, of course. That was so. But here we are not assuming just that u is bounded. We are assuming less. We are assuming that u is bounded, say, from below. Only from below, for instance. So just unilateral bound. Huh? And the assumption is this. So we relax the assumption, we weaken the assumption, and the conclusion is the same. Do you have an idea on how we could show this using the Harnack inequality?
Maybe we can write Harnack inequality for derivatives. Can we write? For example, u is Harmonic. It implies or not. Its derivative also Harmonic. For example, ux1 or something. Because getting constant, we have.
Well, but I mean, you can play with these two constants here. If you are able to put to force this constant to be equal 1, suppose you are able to do, then you get that supposing u of x must be in between u of 0 and u of 0. And therefore u of x must be equal to u of 0. So can you play this constant to be 1? It's not difficult, eh?
Yes.
So what would you do? It's easy to make this constant 1, no? Because you have this, so fix any r, for any r. We have this inequality here, 1 and 2, 2 and 1. Any r and r in 0r. We have 2 and 1 inside the ball, and then how can I let this go to 1? I have the freedom to move my parameters. So what would you do? I have this for any capital R, for any r in between 0 and r, and for any x here. What would you do?
Let R go to infinity.
Perfect. So we have this inequality. We fix small r. We fix x, fix small r, and let capital R, as Rama saying, to plus infinity. So fixing x, fixing r, 0r, x in BR, let r go to plus infinity. If we let r go to plus infinity, we pass to the limit into these two inequalities, and we get, passing to the limit into 1 and 2, we get, so passing to the limit in 1, 2, as r goes to plus infinity, gives us this for any x r. But since this is true for any small r now, must be true for any small r, this means that for any. Okay? And gives the conclusion of this interesting, stronger version of Liouville. Okay, now oh yes, now there is another interesting fact coming out from this Harnack inequality. So let me write it sort of corollary directly related to this. Okay, so theorem, it's another way. So let R positive as before and R in 0R. Then there exists a constant. Now we will see on what this depends, such that loop on BR U is less than or equal than a constant. Yes, if BR U. This depends only on R. But it is independent of, for any non-negative harmonic function U on BR. Is another way to say that the values of U are all comparable in a ball. Okay, so proof. We have to use the previous result. No, so let's fix 2 points. The ball, the small ball. So by the previous theorem, by Harnack inequality, we have the following 2 inequalities. So U of x less than or equal to 1 plus R over R, 1 minus R over R 0, larger or equal, then 1 minus r over r, 1 plus r over r, and the same inequality for the point y. So we have these two chain of inequalities. Now, how can we compare the values of u at two different points? Well, the idea is to concatenate these two inequalities. No? So, for instance, we can start from here. I don't know, u of y is less than or equal than this times u of 0. But u of 0 is in turn less than or equal than this inverse times u of x. No? So since this inequality here pretends to compare the values of u maybe at two different points, the idea is just to take a concatenation of these two. So let's try to do this. So we have, say, u of y less than or equal than this. This by 1. Then we use 2. Remembering that u is always non-negative. So you see the statement, how it is written, says explicitly that this constant is independent of u, because this quantifier becomes before this other quantifier on u, no? So this C is independent of u. So we use now 2. So we copy this. Now u of 0 is less than or equal to 1 plus r to the r minus 1 minus r over r. No? This should give me already the constant. So what do I get? Now I get 1 plus r over r n divided by 1 minus r over r to the n. So this is equal r plus r divided by r minus r n u of x. Okay. So and this, I think, is my constant. R. Okay, now passing to the supremum. Supremum over y gives that sup on BR of u is less than or equal than C times u of x for any x in BR. Passing to the infimum with respect to x, assertion. Okay? Is it clear?
Yes.
Yes, clear.
Okay, perfect. Okay, so now we can still continue in our list of various forms of the Harnack inequality. This has been done on a ball. Now we can do sort of similar inequality in a domain omega. So let's see the extension theorem, say Harnack in omega. So we take omega be open set and take a subset omega prime connected, say, open connected. Okay. Then, sorry, I need some space. Then the same holds same this, and there exists a constant depending on what? Depending on the dimension, omega prime, omega, such that sup over omega prime of u less than or equal than c times the inf of u over omega prime. So it's exactly the same statement, but now instead of having two balls, one inside the other, we have one open set connected, relatively compact, and connected inside an arbitrary open set. Okay? For any harmonic function u non-negative harmonic function u in omega. Again, the way the statement is given remarks the fact that this constant does not depend on u. So how would you prove? How would you prove this kind of statement knowing the previous one? Have some idea? Huh? Do you have some idea? It's not difficult, eh? How would you do? Knowing the previous one and using the connectedness, the compactness of omega prime bar, how would you do?
You take up all the contents.
Okay, let's try to do this this trick. So,
If omega prime is compact, then we can cover it for finitely many, for example, balls or something.
yes, exactly. This is one idea. one idea is to, so first of all, omega prime bar is connected and open, therefore it is pathwise connected. So given to any points can be connected by a path inside, but not only that, omega bar prime is compact, so we can cover it by a finite number of balls. So on each of these balls we have previous inequality, so these balls must be self-overlapping. The distance between omega prime and the complement of omega is positive. Positive, okay? Distance is positive, and well, let me call it 4R. 4R, just as a notation. So I have, this is my omega, this is my omega prime. Then I take 2 points, x and y.
Professor, what will happen if this distance equal to infinity?
Sorry?
If this distance equals to the infinity, what will
be even better, would be even better. Okay, if you it is even better if omega is very far, but okay, if you want, we can do this bounded. Okay, so take 2 points here, and with their distance is less than r, say. So this is for r. Then you have 2 points at distance at most r. Then we consider a ball of centered at x or radius 2r. Okay, so 2r, ball of radius 2r. And then, okay. So a ball of radius 2r centered at x is surely contained in omega. By our choice. So as you see, if this distance, okay, so what do we have? Here we have that we have that u of x is equal to its mean value volume mean value formula (1 over 2n omega n r to the n. Then, okay, we know that y is contained in this ball because this distance is at most r, and also the ball centered at y of radius r is still contained in this ball, no? Okay. Is this the, no? Because their distance is less than r, then I take a ball of radius r, this radius is 2r, and clear? Is this clear?
Yes, Professor, it's clear.
Maybe I should write. So this distance is less than r. Then I take a ball of radius 2r. Then I have a point here. Then I take a ball centered at y of radius r again. What I'm saying is that this second ball is always contained in the ball of radius 2r. Okay. Why I'm using this? Because I say that the integral over b to r x of u x is always larger or equal than ry u. Is this clear? I should use another symbol here, dz. Why? Why?
U is non-negative.
Why? So this is clear, but why this is true? Why the integral of u on a double ball must be larger or equal than the integral of u on a small, why the integral of u here must be larger than the integral of u here? Why? General is false.
It's a positive function. We can separate the first integral.
No.
Two parts.
No, it's trivial once you remember that, once you remember our assumption, no? Non-negative. Negative functions, it's trivial. Just one has to remember the fundamental assumption. Okay. Because u is non-negative. Okay. Now we write, as I was writing before, u of x is the volume in value of u on this doubled ball. So let me separate this 1 over 2 to the n, write it separately. Then I write it 1 over omega n r to the n, integral b to r x u dz. Sorry for the notation, z everywhere. Okay. U of z dz. Now, as we have observed before, this is larger or equal than this. So by inequality 3, this is larger or equal. So let me copy this prefactor here. And let me copy also this. Omega n r to the n, then we have b r of y, u of z, dz. Now, so this is the volume in value formula. Rx. This instead is the inequality 3, and now I am going to use the volume mean value formula in the other ball, the ball centered at y, this ball here, okay? So using the volume mean value formula in B R y, this gives us u of y. Okay. This way we have more or less compared u of x. So, and then u of x is larger or equal than 1 over 2n of y less than or equal than 2n of y, because then once I have done this, I can exchange the role of x and y. So if you accept this, then I exchanging x and y. So we have that u of y is larger or equal than 1 over 2 to the n u of x, which means u of x less than or equal than 2 to the n u of y, which is what I have written here. Okay? So this we have obtained. And this we have obtained for any x and y into for any x and y in for any x and y in omega prime at distance for n x and y in omega prime x1 minus y less than r. Is this clear up to now? If there is something which is not clear, please stop me immediately.
It's clear.
It's clear.
It's clear for me.
Also for AMA, for everybody?
Yes.
Perfect. Now, this has been obtained only for pairs at mutual distance. So the situation is there is omega somewhere. Then we have this strange job that, I don't know, this omega prime. And we have an estimate for points, pairs of points at mutual distance less than r. Now I want to make this local estimate into a global estimate on omega prime. So I can use the following. By assumption, omega prime is open and connected, therefore, given 2 points, even far from each other, x and y, this open and connected is pathwise connected, so I can always join them by a path, but also omega prime bar is compact, so I can find a finite number of balls essentially covering all the omega prime, and in each ball I can do the estimate, no? So taking the 2 pairs x and y arbitrary in omega prime, so what do? I cover omega prime by the finite number of balls, omega prime bar by a finite number of balls. Okay? Cover omega prime by a finite number of balls of radius r. Radius r, see? Then take any point, take x and y in omega prime, connect, and we can also assume that these balls, of course, are, so let us call them, I don't know, B1, Bn, and we can assume that Bi, they are ordered in such a way that Bi intersection Bj is non-empty. Sorry, Bi plus 1, say. Bi for any I. So the first intersects on the second, etc., etc. Then you take pairs any point omega prime, take a path, a continuous path, gamma connecting gamma inside omega prime, connecting x and y. So what do? You have, this is x, this is y, then this is your gamma. Then surely you are in this situation. No? So what do? Here you take a point, and here you have an inequality. Then you take this point and another one, etc. So you have an inequality in each of the balls. So at most, and you lose each time this quantity. No? So what
Final inequality, I think, 2
yes,
degree, 2 n multiply n,
yes.
big capital.
B1, B capital N. Yes, exactly.
But one thing, Professor, it also depends on the large n. Our C, then our C universal constant must be depend on capital N, right?
Yeah, what I see, it seems to me that this should be true. This is correct?
Yes.
No?
So I think we get that balls overlapping, that B1, B capital N. We get this balls such that that is minimal number of balls that satisfies this condition.
But
then
it is clear that we get this, and each time we do a step here, we lose a constant of this form, and we do this step capital N times. So we should have this, essentially, this kind of inequality. Now, for any x and y, however, not close to that, not necessarily close to each other, but for any x and y in omega prime. And now that we have this for any x and y in omega prime, we can take the supremum over y and the infimum over x as before, and we get this with some constant, which depends on what? The dimension?
N.
Yes, it's correct, I think.
Yes. Capital N, big N depends on omega prime and omega.
Yes.
If we get its minimum, the smallest one, then it's
exactly.
well-defined function.
So, summarizing what we have seen up to now, just let me summarize. We have seen a first Harnack type inequality bounding with two balls, concentric balls, bounding the value of u of x in the smaller ball with respect to u at the center. Then we have seen another inequality which was comparing the supremum and the infimum in two concentric balls. More or less was almost immediate consequence of the previous one, just concatenating two of these inequalities. And the same kind of result, where now instead of having two concentric balls, we have two bounded open sets. One omega prime is compactly contained in the other, and omega prime is connected. Okay, so this is the second is clearly a generalization of the third is clearly the generalization of the second. So this is what we have seen up to now. And now let's see, we'll start with the consequences. And then I think we will have all tools to go to study the Perron method for the solution of the Dirichlet problem. But it is interesting. We have already seen, sorry, in my summary, I forgot the Liouville. We have already seen one interesting consequence of this inequality. The Liouville theorem for bounded below, for instance, harmonic entire functions. Okay, now there is another list of consequences that I have to tell you. In some order. One consequence is the following corollary. is a corollary that we will not use in our Perron method later, but I think it's interesting to say. So it's related to another sort of maximum principle called the Hopf maximum principle. So let U to R be harmonic. Take a center somewhere, harmonic, and suppose that let star, the boundary of BR, be a point where U is minimum value. Minimum point of U on BR. And so the constant here is apparently 1 over 2 and minus 1. So minus du over d nu R at the minimum point U of x star the constants. Sorry, the minimum is positive, so x star. Constants are correct. Okay, what does it say? So this it says something like this. I have a function, an harmonic function with drawing is terrible, but I have a point on the boundary here. What I'm saying is that I am reaching the boundary with normal derivative. So this is a minimum point, no? I'm not reaching the boundary like this. I cannot reach the boundary having a sort of horizontal tangent plane here. I'm reaching the boundary at the point of minimum where U is minimum, where U is minimum. So this is x star. I am reaching it with some slope, with some positive slope. So this is this nu is outward, so I'm going toward. I'm strictly negative, unless u is constant. No? You have a similar statement for point of maximum. So if you go to a maximum point, then you have to have a certain slope when you attach to the boundary of an harmonic function at a maximum point. Okay. Sort of I don't know how to draw it, but okay. So let's see the proof. So this is related to some kind of Hopf maximum. I don't know. I don't. Now, we want to apply Harnack. So, but to apply Harnack, we have to take a non-negative harmonic function. So let me call it V. V of x is, by definition, is u of x minus u of x star. Okay, for any x in the closure of the boundary. Now this V, it's clearly harmonic because just U minus a constant, minimum value of U itself, and also is larger or equal than 0. Because this is the minimum value. So V larger or equal than 0 and harmonic. Okay, so it is to this V that we want to apply the Harnack inequality, the first theorem, theorem 1. Okay, and what do we get? So let me write down here the Harnack inequality. It was 1 plus R over R. Okay. Now I use it with the interesting X. Zero. Larger or equal than V of 0. V of x0, sorry. Because the center now was called x0. V of x0. X minus x0. Okay, let me do it at the origin. Uh, 1 minus x over r divided by 1 plus x over r n minus 1. Okay, maybe I can leave it to you. Home. Time is really running. Show using this actually. Using this, show that u of x, that our v of x, that was u of x minus u of x star. Now you see, we divide, the idea is u of x minus u of x star, now we divide by this. Divided by r minus x. This turns out to be larger or equal than, so check this inequality, just copy here. It's easy, just a plain application of u of x naught minus u of x star divided by r minus x. Then show that here you use this inequality and you should get 1 over 2 to the n minus 1, exactly what you want. Okay, so just use this inequality with the correct expression of v. Divide by this. Put it here. Bound from below this. This instead of x, since x is less than r, this is large. This one or this is larger than 1 over 2r. And you substitute r in place of x using the inequality, and you should get this constant here. So this happens to be true for any x. So you have this sort of information. Now what do you do? Well, what is the situation? We have a ball. have a ball. Here you have x star, which is a minimum value for our u. No. Know how to draw? This is the graph of u. Huh? We have bounded u of x minus u of x star divided by this. So this difference quotient in terms of some constant, which is exactly the constant that we want. And then what remains to do, in your opinion? So we have bound the difference u of x minus u of x here, this minus this, divided by this. And instead of this, we want the normal derivative here. So what would you do in order to pass from the inequality that we have here to the inequality, similar inequality, to minus the u over the nu? What do you think? This is not difficult, no? What do you do? So I leave you to do this. The idea is to passing to the limit. So what is the idea? U is very smooth. So here we have x star. Here we have x. Some x, say x. This is x naught, this is the origin. We have controlled from below the value of u here minus the value of u here divided by r minus x. And now the idea is to take exactly that inequality and do it. So here you have a normal. So you can take the inequality along this line. So u of here minus u of here. And then let x converges to x star along this line here, the normal line to the boundary of the ball at x star. Okay. X is in the ball. So just take to the just pass to the limit of inequality inside this direction. So the different quotient here is nothing but the limit of the difference quotient, since the function u is very smooth. The limit of the difference quotient along that direction is the normal derivative at the point x star. There is the problem of the sign. I hope that the sign is correct, because we are taking now this minus this, and not this minus this. No, so it seems to me that this minus is correct, because nu is outward. I don't know if I was able to explain to you. Did you understand?
No, we can understand.
You have not understood?
No, I understood. I understood.
Yes, and Rama also, or not?
Yes, it's okay.
It's okay. So this fill the details at home. I think. I missed something. I missed some comment. Are there comments? No. Okay. So the details, you can fill it, but I think that more or less just, well, you have to fill actually you have to compute this. This is almost immediate. From this to this is immediate. You have to use the Harnack inequality. Maybe you have to check the constants here. Okay, and then you pass to the limit along a specific direction. So it's very interesting, in my opinion, that this Harnack inequality gives us this sort of behavior of the normal derivatives at minimum and maximum points on the boundary. It's a consequence of the Harnack inequality. So at the end, the Harnack inequality seems to be very, very strong in view of the consequences that it has. Another consequence. Another consequence that I would like you to think about a little bit. Consequence. The strong maximum principle. We have already seen this, but let me rewrite it, because this we have seen inside a proof of a another big result. But let me isolate it separately, even if you already strong maximum minimum principle for harmonic functions. So you have, say, remember, when we have strong, we don't need omega to be bounded, but we need it to be connected. This was already remarked when we saw this for subharmonic functions. Okay. So let omega be be connected. U harmonic omega. U harmonic and non-constant. And so this is important. We know that an harmonic function, say, attains, the maximum value is attained at the boundary, the minimum value is attained at the boundary, if omega is bounded, say. But we cannot exclude that there are other interior maximum or minimum points. Instead, we can exclude then you cannot obtain interior maximum and point and minimum points and minimum points. Cannot attain, which means that equivalently, if you have two harmonic functions, one above the other, they cannot touch at an interior. They sort of they cannot touch at an interior point. No? This cannot happen. For if you have this harmonic function here, this other harmonic function here, and this is above, not below the other, unless they are equal, they cannot touch at an interior point. This is what that theorem says. They repel, in some sense. Inside, they repel, in some sense. Okay, so this is, do you remember also the proof? Maybe you should redo by yourself. But we have seen already this proof, because this proof was based on the volume mean value formula, for instance. So we remember the proof was call M the maximum value, the maximum value of U, and then consider the two sets. Now, do you remember? I think B U equal to M. We saw that these are two non-empty. So this is open easy, is non-empty easy, because U is not constant. This B is non-empty easy because it has a maximum interior maximum. And then we have to show that also B is open. They are disjoint. And then you have to show that B is open. If this is true, then this is impossible because omega was connected. No? This was the proof, and the same for a the same for a minimum point, the same proof for a minimum point. So we did this for a subharmonic function, speaking about only maxima. So our proof was more general, but the same proof. So check this proof at home. This is easier, simpler case. We check at home. Okay, this was the strong maximum principle. What I am saying is that this result, and this was based on the use of the some mean value formula. You remember? Do you remember? It was based on the use of the mean value formula. Can you remember?
Yes. We can remember.
And now, always in the idea that we would like to find results which somehow are independent of possible mean value formulas, because this mean value formula seems to be really something related to the fact that we are using the Laplacian, or if you want an elliptic operator with constant coefficients. I don't know, but I mean, very strictly related to Laplacian. The idea would be, how could we get sort of a strong maximum principle which is so expressive, like if you say it in this way, no? They cannot touch unless they are equal inside. How can we, could we prove such a kind of result making use of some other technique in place of the mean value formulas? And one of these is the Harnack inequality. So I would like to give you so proof consequence of Harnack inequality. I would like you to think a little bit about this. So consider, so M is the maximum, okay. Consider a fix epsilon positive. Consider V equal M plus epsilon minus U. And then try to apply Harnack. So now clearly, again, this is harmonic. This is a constant. This is harmonic. But now it becomes positive, okay? Because M is the max. Okay, then try to apply Harnack to some omega prime to V. Okay. This I leave you as an exercise. And finally, I can state it, just state it, another final important consequence. Sorry, time is really another corollary. So this was a corollary in some sense. Then we have another corollary. Maybe I don't know. Maybe I could do the proof next time. I don't know. I will see. I don't know. Okay, so let omega be connected. And suppose that you have a sequence of harmonic function sequence monotone of harmonic functions for which you know just that, so you know that first of all they have this kind of monotonicity, and you know also that there exists such that this is monotonic and there exists one point in omega such that the limit as h goes to plus infinity UH of x naught is finite. You just know, well, you have this monotone. Okay, this will be, this corollary will be used in the Perron method, if there will be time the next time to speak about it. So this is really important in the Perron, so let me used the Perron method. So this was, strictly speaking, just what we need. And then I conclude the statement, but this will be needed in the Perron method. Instead, this was just a curiosity in the sense of trying to do something without the volume in value formula. And also the Hopf. So this is not needed in the Perron method up to now. And also the Hopf, the effect on the normal derivative will be not needed, okay? Okay, then we have a compactness of this class. H converges on uniformly on compact subsets of omega to a harmonic function U. Harmonic function U. Okay, also this I leave you home. Clearly difficult. All these things are non-trivial consequences. So I just ask you maybe not to do this because too difficult, but to think a little bit how could be possible to prove. We will see the details the next time, and which, however, unfortunately, will be the last. I think that on Monday will be the last lecture. So we do what we can. Okay, so thanks and see you on Monday. Bye-bye.
Okay.
Thank you.